All right, welcome everybody to this week's webinar. It's a collaboration between the University of Queensland and the Geological Survey of Queensland. I'm really excited this week. We're doing magnetotellurics in exploration. It's a subject that I personally know nothing about, so I'm going to have my learning cap on. We've got a diverse range of speakers, leading off with Naser Meqbel who's joining us from Germany. So, you know, it's really privileged to have him involved, world-renowned MT expert. We also have our own fabulous Janelle Simpson from the Geological Survey and one of Australia's leading industry MT experts, Shane Evans, who's going to talk about an industry-specific application. So just a quick reminder that after the webinar from about 4:30 to 5, we will have online drinks. So please stick around, join us for an active and lively discussion about what you might have heard throughout the webinar, and it's an opportunity also to ask more questions and have more discussion around the speakers' topics. And if you do have any questions, please feel free to write them in the chat function or in the Q&A function, which you'll see at the bottom of your screen, and we will read those out at the end of each talk. But also a plug for next week, we will have again an international lineup looking at metal isotopes in exploration. So we'll have some smart people come and tell us about that as well. But without further ado, I'm going to hand over to Naser. So please take it away.
Yeah, good morning everybody, or good afternoon, or good evening. And I don't know if you can see me. Yes. Yeah. Okay. Okay, so good morning everybody. And first of all, thank you, Helen and Janelle, for the invitation. And it's my pleasure to be part of this webinar. And I hope that I will be able to present something which is useful for everybody. The main topic that I will present today in my talk is discussing and showing some of the 3D inversion result obtained from East Tennant MT dataset in Northern Territory in Australia. And the major point of this talk is to look and give more information from various datasets. My apology that I'm using some abbreviation here like Z, TZ, and BT, but later we will see the meaning of these letters and data type and see their effect on the 3D inversion or any kind of inversion in MT. So based on some comments and messages I got a few days ago when this webinar introduced, I thought maybe I should give a quick introduction into MT methods, because I thought that maybe some of the audience are not familiar, and to get everybody on the same page, it is appropriate to give like a few words about MT, and it will be like just like 5 minutes, a few slides before we go to the real application using the East Tennant MT dataset and discuss the 3D, specifically 3D inversion from the various data types, namely full impedance tensor, Z, full vertical magnetic transfer function, phase tensor, and a combinations of all of these. And finally, I will give a conclusion, and we will discuss a few things. Yeah, magnetotelluric, which is the main topic of this webinar, is part of other electromagnetic methods in geophysics. And as you can see here from this chart, there are few electric and electromagnetic methods. And as, all of them is applied to image one single physical parameter or property of the subsurface, namely the electrical conductivity. These EM methods can be grouped like passive source or active source. Active source is man-made source that you inject energy in the subsurface and you measure the responses. While in passive source methods like magnetotelluric, we don't have a transmitter. We use the natural EM wave that is coming from the ionosphere. Now, since we are talking about the electrical conductivity of rocks, this textbook's chart shows the variation in the electrical resistivity or its inverse conductivity. So during this talk, I will use either conductivity, Siemens per meter, or resistivity ohm per meter. But this chart shows you how is the variation in the conductivity of the rocks. That varies, for example, from a few hundred Siemens per meter, that is for superconductive material like massive sulfide, graphite, to some extent also seawater. And we have in the middle some middle range of conductivity or resistivity rocks. And to super resistive material like unfractured or unweathered metamorphic rocks and other type of rocks. So most of them, they are resistive. And in the middle, as you can see, we have like shells, clay, sandstones. The major point here is that the porosity plays a major role, and the material that fills this porous is casing the conductivity anomaly in our electric and electromagnetic methods. Has been said, I mean, when talking about the electrical conductivity of the rocks, we are talking about the material that fills these pores or fractures. And this material could be fluids, could be ores, could be milled graphite or sulfide. And if they are interconnected on a larger scale, they cause such kind of conductive anomaly that we will talk about and present it using the magnetotelluric method. Now, on the magnetotelluric methods, one question is, what is the source of the natural electric EM wave? So we have several sources, namely solar activity, that interact with the ionosphere and creating a current system in the ionosphere that propagate downward to the Earth and creating or induced electromagnetic fields that we can measure. The other source is lightning, and looking at this, the period or the wavelength from these two kinds of natural electromagnetic source, we can distinguish between long period data and short period data. And they are very important in our measurement or magnetotelluric measurement. Sorry. Now, once this EM wave created in the ionosphere and start to propagate in the subsurface, it changes in the amplitude and phase, and it penetrates into the Earth. And the penetration depth of the EM wave depends mainly on two parameters, namely the subsurface conductivity and the period at which this EM wave penetrates into the Earth. So in summary, one can say for long period and resistive background, we will get a deep penetration. While for short period and conductive subsurface, the penetration depth is very shallow. And that's what we call in our community the scan depth effect. To look closer on...
Naser, can I just ask?
Yes.
On the bottom of your screen now, there's where the video panel is. We've got a bit of a blacked out section. Could you move that video panel away so we can see your whole slides?
You mean this?
Yep. If you could just move that maybe to another screen, that'd be great.
Is it okay now?
That's much better. Thank you.
Yeah, sorry, I was trying to move that because also I cannot see the part of my screen. But anyway, I hope that it is better now. Okay.
Much better, thank you.
So, Yeah, talking about the natural EM wave, and this animation simply shows an electromagnetic wave that is generated in the ionosphere. What we are looking at is the lower part of the atmosphere. So the energy or the EM wave is generated above or at the top of this model, and as you can see here, at some level, the EM wave is isolating in east-west direction in this animation, and the propagation is downwards. And once this energy penetrates in the subsurface, where this white line is marked, then you can see that the electric field change in amplitude and phase. In this animation, it's a very simple animation, is what we have here in the subsurface, a conductive material to the left, where we have this blue colors, and we have resistive material to the right, where we have like orange to red colors. The point is here that, as you can see, and as I explained before, that for a given period, this is here, by the way, 10 seconds, this EM wave is penetrating in the subsurface. You can see that in the conductive quarter space here to the left, the energy is decaying very fast exponentially, and what we can see only part of that at the top of the subsurface. While in the resistive part here, we see that the energy penetrates very deep, and we still see a high amplitude of the electric field in that part. But interestingly to see that even at the top of that surface, we see how the electric field change in phase and amplitude close to the conductive contrast between the conductive and resistive spaces. Now, imagine that you put a sensor somewhere at the top of the surface. Let us look at that triangle here. And you have the required instrument to measure these time variation of the electric and magnetic field. So that is that's how we do the magnetotelluric measurement or MT measurement. So this animation shows you a field setup or a site at which we measure the time variation of the electric and magnetic field. And usually, to measure the electric field, we use two pairs of electric dipoles. They are orthogonal to measure the variation in X direction and in Y direction. Okay, so the X and Y direction could be any direction, but the major point that these two components, this should be orthogonal. In addition, we use induction coils to measure the time variation of the magnetic field. Again, these also the horizontal component of the magnetic field should be orthogonal and parallel to the corresponding electric field, as you can see here in this animation. In addition to the horizontal component of magnetic field, we also measure the vertical component of the magnetic field. And as you can see here, this coil here is in the penetrating in the subsurface. At this point here, I should say that it is very important comment that for somebody who is going to work in MT, and keep in mind, I mean, this is the first step towards having MT data and the interpretation. So my recommendation here is that, and my comment on that screen here is that acquisition, which includes also setting up the site in a proper way, is that important as the other steps toward imaging the electrical conductivity of the subsurface. Typical mistakes at this step here that cannot be repaired or cannot be covered later in any software or in the office, something like the horizontal component are not orthogonal, or BZ is not completely vertical, and the coils are not well buried. So you will get something like temperature variation that affect the coils, or someone that could move the coils and don't have them orthogonal completely. My comment here is really, I mean, setting up an empty site is that important as the other step later during the workflow for the processing and modeling and interpretation of these data. Now, once you have collected the time series of the electric and magnetic field, this figure shows some time series, the traces, and usually in the field, people look on the signal on each of these components and do some QC in the field in order to decide whether these data are usable or one needs to recollect the data at some specific site. But the point here is we collect the time series. We run processing tools on this time series. And talking about the processing tools and the time series is a completely different word, okay, and requires much more time to explain that. Let us use that as a black box, what's happening in the processing tools. But generally speaking, is what we are doing is converting from time to frequency domain, applying some filters to end up with the data that we will use later for the interpretation and modeling of MT data. The first data type that typically used in MT is the so-called impedance tensor. It is nothing else than relating the horizontal electric to the magnetic field via a transfer function. That's what we call impedance tensor. And this tensor, impedance tensor, carries information about the electrical conductivity of the subsurface. And here keep in mind all the quantity are a function of period that's expressed here in omega 2 pf. Okay. The other component or the other data type that can be obtained from these 5 electric and magnetic component is the so-called vertical magnetic transfer function, or TIPR or TZ. And this is nothing else than relating the vertical component of the magnetic field to the 2 horizontal magnetic component. And usually we call it TIPR, and the name comes because this ratio shows how much is the vertical component is tipped in the vertical direction, and this is why the name TIPR. The other data type is not directly derived from the time series, but it is derived from the impedance tensor, the complex number. And you can imagine that the so-called phase tensor is like taking the phase of that complex number. And it is, as you can see here on that tiny equation, is the real part of the impedance tensor that is derived from the first equation here to the imaginary part of that component. Now, why I'm introducing and giving a quick introduction to this data type, because these are the data type that I will use in the application when using the East Tennant MT data. And I will show some 3D inversion results using all of these data type and also a combination of them. Now, the application itself, To the application itself, the East Tennant MT dataset from Australia, which is currently distributed and made available by Geoscience of Australia. When they published this dataset early this year, I thought maybe I give it a shot and look at this data and try to train my brain in the 3D inversion of MT data. Because as we will see later in the conclusion, each dataset has its own characteristic. And for me personally, for example, I like to train my brain all the time, looking at different data sets and see what is the characteristic and how can such kind of data interpreted and what kind of steps required to do the interpretation. On the location map, the study area is located in Northern Territory and Northern Australia, and the survey covers around 100 times 100 kilometers. In total, there are 131 empty sites, and the 5 components are measured. And the data are in broadband plus audio magnetotelluric data. So the period range goes from around 10,000 hertz to around 10,000 seconds. So the time series are processed to obtain the impedance and tipper data. And as I said before in the previous slides, that the phase sensor is derived from the impedance or Z data. So in total, there were 88 periods in this data set, but for 3D modeling purposes, I downsampled this data to 24 periods without losing information from this data. If somebody is interested to know why I do that, I am happy to discuss this point and show and justify that 88 periods are usually not required to make 3D modeling or interpretation of the data. In terms of quality, the data are good to very good. Data acquisition done by Zong engineer contracted by Geoscience Australia. And these two links shows other metadata about the data, and you can obtain this data from these two links. Yeah, looking at the data, I will take a cross-section or pseudo section along this white line here, as you can see on the map here, and just to show to start looking at the data, which is the first step in any kind of interpretation. So first you need to look at your raw data and see if you can figure out the meaning of this data before entering any kind of inversion, modeling, or whatever you want to do with the interpretation. So my recommendation here, looking at the data, understanding your data, is one of the major points that should be considered before doing any kind of inversion. Now I will show you a pseudo section along this white line. White, not pointing. Okay. Yeah, sorry. Yeah, the upper, here are two kind of pseudo section, and usually the impedance tensor is presented as apparent resistivity and phases like sounding curves for each component in the complex impedance tensor. And here the upper panel shows the apparent resistivity and phases of the off-diagonal component that is called ZXY, and the lower panels are for ZYX. X and Y are standing for the horizontal component of the electric field and magnetic field. So for ZXY, we are taking the ratio between E in X direction and B in Y direction, while in the in ZYX, we are taking the ratio between the electric field in Y direction and magnetic field in X direction. Basically, when looking at this phase tensor, in the pseudo section, the upper panel is the apparent resistivity, here is the phases. We look and see the quality of the data, and also to see if there are consistency between the neighboring sites. And as you can see from this pseudo section, there are a correlation between the adjacent sides. So one can say, okay, one can get some useful information from this data set. This is the impedance tensor presented as a pseudo section. One can also look at the other component of the data, namely the tipper data or the vertical magnetic transfer function, which is presented as usually as induction vectors. And at the top left map here, we can see the tipper data at 100 seconds. And usually, I personally, for example, use such kind of maps in order to make the first interpretation of the subsurface. And if you look on the physics behind the taper data, they usually point to high concentration where we have high concentration of the current, electric current. And they point to that high concentration. And if we are talking about high concentration of the current, means that we are talking about conductive materials. In that figure here, at this period, at 100 seconds, we see that most of the induction vectors at this part here in northwestern side, they point toward the center of the array, meaning that we have some conductive anomaly that is running in the center of the array. While in southeast stations, we see that they, at this particular period, some of them, they point toward the center, like in the southern sides here, and some of them, they point to north direction. So generally speaking, at this period here, one can imagine that there is some conductive anomaly running in the center of the array casing, that the induction vectors pointing to that anomaly here. The phase tensor are usually presented as ellipses, and one can take a look at the ellipses at various periods. To be honest with you, I am not that familiar in interpreting the ellipses themselves. But when looking at the sounding curve of the phase tensor data, one can derive some information. But what we usually use these phase tensor ellipses is to study the dimensionality of the data. Again, at this period here, at 100 seconds, we see that most of them, they show data, which is a parameter derived from the phase tensor computation, and deviation from zero giving an indication of the dimensionality of the data. So something like -4 or +4, this is in this figure here, meaning that we are dealing with more than 2D subsurface or higher dimension of the data. That was the introduction to the empty data, and that I will use later in the inversion process that I will show and discuss with you. Just a quick background on the empty sites that we will deal with. And I'm pretty sure that some of the audience are much more familiar than me with regard to the background of this dataset. But what I've understood and read about this dataset is first, the Ausland data were inverted, and they got that image here to the left of the screen. And they observed a high conductive anomaly that is located in that part here. And based on that, they decided to make a high dense empty array in order to better understanding the conductive structure in that part of the region. And by the way, this conductive anomaly is like making a corridor that goes further to the east to Mount Isa. And I guess it is the topic of our colleague Janelle Simpson, who will present the talk about that later. So that is a general background, and that's what I understood from this data. Maybe somebody else can add more on that, but I will go directly to the inversion of this dataset. As kind of data that I will use during this comparison process and comparing the 3D conductivity anomaly with other geophysical data, the only data set that I found and I can compare with is gravity data, also published by Geoscience Australia. And here is a map showing the free air Boger anomaly from the gravity data, overlaid with the empty sites, the black triangles, and there are some lines here. They are presented or interpretation of faults. And in my understanding also, they are derived from the gravity data. So the information that I will use to compare with our conductivity model are the location of the faults in that map here, and also the amplitude or the value from the free air Boger anomaly. So most of the time, or all the inversion process, the sections that I will show are along that AA prime section, where we have a high and low amplitude of the free air Boger anomaly. And I will overlay the conductivity model with this data in order to make a better interpretation, or to try to interpret the data based on this reference information that we have. And also to facilitate the presentation here and not going back and forth for the conductivity model and comparing with the gravity data and the fault location, I will use a map view at around 60 kilometers, which is like a middle crustal level. And I will show a cross section along this white line. And at the top of the section, I will show the gravity anomaly, presented here as black dots. And the intersection of the conductivity section with the fault lines are presented at these red arrows, if you can see them at the top of the section. So we start inverting and looking at the data, or at least the procedure that I use is to invert the data individually. That means if I have impedance, if I have tipper, and if I want to use the phase tensor, I usually invert them separately. And the point here is to better understanding which data type requires which structure in the subsurface. And keep in mind that what we are doing during the inversion process is nothing else than projecting from the data space, the data that we measure, into a model space, the one that we will use for the interpretation. And also remembering that each data type is sensitive to a different kind of structure or contrast in the subsurface. It is much more appropriate to consider and looking at the inversion result from these individual data types. And that's what I'm doing here. And later we can combine these data type in order to improve our subsurface images. On this figure here, what I've used are the impedance tensor data, only the impedance tensor data, the full impedance tensor. And as you can see here, most of the structure are resistive. If you look at that depth slice at 16 kilometers, we see a lot of resistive material. And at some places we have, at this specific depth, we have some conductive anomaly. And by the way, the color scale goes from 1 ohm meter to around 2000 ohm meter in a logarithmic scale here. So red and orange colors are for conductive anomaly, while light to dark blues are for resistive anomaly. And on the cross section here that you see to the right of the screen is we also see that most of the structure in the crust are resistive, aside from some discontinuity that we observe, for example, where we have the location of the faults, specifically that one that is located to the right of the section. That was only the full impedance. Now, looking at the tipper data alone, the figure changes, and as you can see here, we see much more conductive material at the same depth level at 16 kilometers. And if you look here carefully, we see that elongated conductive anomaly that are oriented in southwest to northeast, and most of them are located at the center of the array. And if you still remember the induction vectors, they are pointing to some conductive anomaly in the center. That's at least what we read from the raw data. Now comparing that, the 3D model from only tipper data with the gravity that is at the top of the section, we see that there are some correlation between what we see in the gravity, these two peaks in the anomaly, and the conductive material that we see and got it from inverting only TIPR data. Of course, I mean, TIPR data, they don't give a good image of the subsurface with regard the elevations or the depth of this conductive anomaly. And usually what we do is to combine impedance tensor and TIPR in order to improve the subsurface images. And that's what I have did in this slide here. Now, combining the impedance tensor together with TIPR data, we will get another different images here. And if you correlate with the location of the faults on the map view here, you will see that there are a good correlation, specifically with that the central fault line, as you can see here. It is located where we have this contrast between a resistive material in northwest and conductive in the center, and again we have a resistive material in southeast. So this conductive anomaly is sandwiched between two resistive blocks. Looking at the cross section again, we see that one of these high gravity anomaly, that this peak here, is correlated where we have this conductive anomaly in the section. And comparing with the fault lines, we see that is a good correlation with the central fault that is presented as this red arrow here. Now one can stop at this point and say, okay, I'm fine with this interpretation, there are a good correlation. And also if you see this fault line here, if you see my mouse, there is also some contrast that can be interpreted in correlation with the fault lines and the gravity data. One could stop and say, okay, that's good here, and we can start making some interpretation. But I didn't stop at this point, and I wanted to know what is the phase tensor can provide us in addition to this picture here. And what I did is inverting only the phase tensor data. So the audience who are familiar with that, and they could argue that the phase tensor doesn't give a good information about the depth location of such kind of anomaly. I kind of agree with that, but we're looking at that such kind of figures here, specifically on the map view. You see that the fault lines, especially the one that is located in northwest of the array, is much better mapped here. And we can see that there is a conductive contrast where we have this fault line, which didn't appear if you look at this figure here, using only impedance and TIPR data. While including or using the phase tensor, we start to see that there is some conductive anomaly located in this part of the model.
Now, I'm just going to give you a time warning.
Yeah, just like a few slides and I will finish.
Right, no worries.
Thank you. Okay, so looking at the fault location again, derived from the gravity, we see that this conductive anomaly that is located in northwest direction is correlated with that peak in the gravity data and where the location of that fault line. Okay, now how about if we combine the phase tensor with TIPR data, and that's what you will get. If you combine now phase tensor and TIPR, the conductive stripe that is observed in northwestern direction is improved a little bit and follows exactly where we have the fault line. If I switch back and forth between phase tensor only, phase tensor plus TIPR, you will see that these conductive anomaly and resistive stripes are now elongated in southwest to northeast direction. And they follow the trend of these fault lines. And here is the section shows that the correlation between the gravity and the fault location. At this point, I mean, I will not do any interpretation, by the way, of this data. I'm just sharing with you the experience that I have gained when I work with this data set. I mean, the interpretation should be done and confirm which of these models is fit to the tectonic and geological setting of that study area. So my conclusion here will not be related to the interpretation or any of these figures that I was showing from the 3D model, but rather on a general conclusion point on the 3D inversion. So the 3D inversion of empty data is not straightforward and needs to be done really with a lot of cases. And I've got all the time questions like, okay, is there something general, a script or something that can be used to run 3D inversion? The answer is no. Each data set has its own characteristic, and you need to think about ways and strategies, procedures on how to run the 3D inversion, how to interpret your data, and how to make a better conclusion on the data set. Another thing that I should mention here, that 3D inversion or any kind of dimension like 1D or 2D, they are not magic. You know, I mean, these are, they cannot solve all of your issues. So you need to take that in consideration. And as I said, looking at the data, understanding your data is the first step toward understanding the model that you will get from these data. By this, I would like to thank your attention, and I will leave you with this movie here that shows the 3D model obtained from only impedance and taper data overlaid with the gravity anomaly. And from the resistivity model, I am just extracting few isosurfaces in 3D that they represent a conductive and resistive anomaly. With that, thank you very much, and I hope that I am still in time.
Thank you so much, Naser. That looks fantastic. We do have some questions from David Annetz. Could you comment on the inversion quality? You didn't catch a mention of the error. And
yes, sure.
I'll save the next question. Yep.
Yeah, go ahead. Yeah, I mean, I didn't talk about the if the data or the inversion quality is referring to the data misfit and the error setting. I didn't discuss that here because I fixed these values and I was focusing on the structure themselves and see the differences between various inversion setting. But for the error, I'm using, like if you are familiar who asked this question, I'm using 20% of the diagonal component on the impedance tensor, fixed values on taper and phase tensor. And by the way, in all of these inversion runs that I have showed individually and jointly, I was using the same error setting. So I'm not changing the error setting to make this comparison valid.
Okay, and then one more question. Could you comment on the effect of model discretization?
Sure. It is one of the major issues that we have. I mean, model discretization, I like a comment from John Booker, who said once that discretization of the subsurface is alone an art. So you need to know how to discretize your subsurface. I usually use some criteria from the data in order to discretize the subsurface. Something like the scan depth and see what is the lowest apparent resistivity in the data, and based on that I can discretize the model in the vertical direction and in the horizontal direction. Another thing is if you want to include topography, if you don't want to include topography, all of these parameters, they affect the way that you need to discretize the subsurface. But believe me, it is not straightforward. So you need to think about how to discretize your model in 3D. Of course, I mean, there are a lot of criteria that can be used, okay? But based on the experience that I have gained over years working with 3D inversion, is these parameters can be derived from the data themselves.